Okay, I think we're recording to YouTube. Hi everyone, it's been a while. Wanted to give a little lecture series of some things that I've been thinking about, some things that I've shared, and hopefully, yeah, and some open questions. And part of this, and I'll come back to this at the end of the talk. Uh, Sarah Peterson is giving a course soon on hop rings, and that's going to be the topic of the third talk in the series. And so I wanted to record this in part for folks who wanted to follow up on some of those ideas. Um, as I said, though, that's going to be the third part. The first part, and the main crux of this is that these Eilenberg-MacLane spaces, and I'll tell you what those are in just a few minutes, they're basic building blocks in algebraic topology, and people think of them as these sort of almost transcendental constructions. I mean, they really generally are made that way, as I'll tell you about. But they're actually spaces where you can think about the geometry, and that's very fruitful. And so for the first lecture, and that's today, we're going to talk about homology and trying to get a handle on the homology geometrically. Second part, I'm going to fill in the story of the bar construction, because really what we're doing is we're giving some geometric thought to the iterated bar construction. And then in the third planned lecture here, I'm going to talk about hop ring structures. Okay, so let's just jump in again. So this is a series aimed for people who've studied some algebraic topology, maybe towards the end of a year in algebraic topology. You don't have to study that much. You don't have to know what Eilenberg-MacLane spaces are ahead of time. Just then maybe trust me that they figure prominently in a number of things. Makes this interesting. So yeah, let's jump in. So the definition I'm going to give for these model for Eilenberg-MacLane spaces, it's going to have a funny name, B delta N A. So A is an abelian group. And let me draw a picture first. It's going to be a cube with points labeled A1 through AK for some points in the abelian group A1 through AK. And what it is I'm going to take the union over all, okay, greater than or equal to 0. I'm going to take an n cube. That's the same n as in the superscript here. I'm going to take its kth Cartesian power. I'm going to also take the kth Cartesian power of A. I'm going to quotient by the symmetric group. So this basically just attaches the points in A to the points in the cube, but says that we don't really care which order we listed them in. And then I'm going to take all of those, and I'm going to have a larger equivalence relation that will go between the k's. So let's just say I've got x1 through xk cross a1 through ak as my representative. And the equivalence relations say that if any ai equals e, then remove ai and xi from the lists. Okay, these are a pair of lists of elements of the cube and elements of A, and just if AI is E, then remove it. In other words, if one of these AIs is E, then we can, well, no sooner do I write it as I delete it. Secondly, if any xi is in the boundary of the cube, then do the same. Okay, so as these points, that you could view them a path as these particles all moving, maybe in time, and if anybody hits the boundary, it goes away. Maybe that we think of them as bugs, and that's a bug zapper or whatever. That's probably seems strange. Let me say now, I might make the comment again that what we can do alternatively is take a sphere, an in sphere and A, and make the same thing. So in other words, we can replace this by Sn. And then the second condition becomes xi hitting the base point and things go away. And that might seem a little bit more natural, more symmetric or something like that. Okay. And then the third is that if there's some if these AIs are moving into these apartments XIs, well, if you share if XI equals XJ, then what we're going to do is let AI, the new one, be the old AI plus AJ, and we're going to remove XJ and AJ. So in other words, really we could, if you want to be more symmetric, we could add in a point there with the sum, say at the, I don't have to put it at the I or the J spot, but in any case, if XI equals XJ, two of these things, if that happens in a path, they collide, then they would add. Okay. And so here's the claim. Is that the homotopy groups of this construction are either just A for the nth homotopy group and 0 otherwise. In other words, for those who know the lingo, this B in delta A is a KAN, is an Eilenberg-MacLane space for A in degree n. It's a space with one non-trivial homotopy group, and that's in degree n, and 0 homotopy otherwise. So let me, for some, this immediately makes these interesting. Some of you probably already know about B delta, but maybe not the geometry of homology as we're going to get to. But for others, Postnikov in the 1950s showed that for any x, I could map it out of a series of spaces. And this tower is canonical in a way I won't make precise. And then the point is that each of these maps, so phi naught is P0 is just a point if X is connected, phi1, phi2. So phi I is an isomorphism on homotopy groups through the ith stage. And the other thing about each of these little triangles, I've got pi x mapping down to pi minus 1x, the fiber of that map is a k I x in degree I. So this tower, these fibers here are Eilenberg-MacLane spaces, and what this implies in good cases is that x um, is weakly equivalent to the inverse limit of the pi x. And so you're assembling x from spaces where inductively I'm building it through these Eilenberg-MacLane spaces. So in particular, then, the way these Eilenberg-MacLane spaces fit together will determine all homotopy types. Very classical view. You could think of these as the chemical elements, and it doesn't suffice to know the homotopy groups. It doesn't suffice to understand these ingredients. But these really are the ingredients, these Eilenberg-MacLane spaces, and you can assemble them to get your X. So let me give you the standard approach to constructing these. So let's let A be just like Z mod M, or CM is maybe what I prefer. And what you can do is you take an insphere. So far, so good. We take a dn plus 1, and we attach its boundary by multiplication by m. That's fine. That's going to get us an nth homology group, which is Z mod n, and no other homology, actually. That's, standard exercise is called a Moore space. But you can have some interesting homotopy groups. And what you just do is, if inductively, if f from some s d to this this y, say j at inductive level j, so this would be my y naught, is not null, then we can attach a d plus 1 disk along f. And what you do is you say take your homotopy generators degree by degree. The next ones would be in degree n plus 1. You might have some homotopy, you kill it. All right, and then you show that you haven't added anything in that degree or lower. So you go to the n plus 2 group of this y1, and you kill that, and you keep on going. And there is some CW complex, which only has one homotopy group. And what I'm saying is, actually, like for, KZ3, you can think of that. It's almost like a little paperweight you can imagine. I'm sure somebody could produce this, a little cube where points are labeled by integers. You've got 57 swimming around, 2, 3. So this is literally up here a picture of KZ3, or at least a point in KZ3, where I have negative 27 labeling some point, 500 labeling some other point, maybe 1 is labeling a point. And, a path in KZ3 would be these integers swimming around a fishbowl almost. And so that's a much more concrete way to approach the space. Now, it's still infinite dimensional. I've got the definition there, in to the k can be arbitrarily large, but those are organized not by some abstract, here we can kill homotopy groups, but through this geometry of this Bn delta. So, right. So these are the building blocks of homotopy types, or at least, finite homotopy types. I suppose I don't know the good group theory beyond finitely generated setting to what extent the Postnikov tower still works if your homotopy groups are horrendous. But in any case, these are the building blocks for much of homotopy theory. And a question is, what is their homology? Sorry. And the answer was calculated, it's remarkable, by Cartan back in the 1950s. But there's a few things which make this less than satisfying for current practitioners. First is that it's never translated to English that I know. I'll put that as a question mark. And I do speak French and I've read them, but it definitely for some that makes it a little bit harder. Second is that the primary approach is inductive. And so there's room for, and the point of the lecture today will be the question of more sort of direct or explicit combinatorics. And finally, there's absolutely no geometry in what he does. He sort of has these inductive spectral sequence calculations, and there they are. Okay, so this first lecture, I'm going to take you through just some limited homology calculations. We're going to focus on the abelian group being the cyclic group of order 2, and we're going to use mod 2 coefficients. Okay, so let's again draw our picture. B1 delta C2 is a space where I can take a bunch of points in a delta 1. I'm going to label each of them by, well, an element of the group of order 2. Now, if any of them is the identity, I can erase that label, okay? And so you see that there's, that all I have to do is specify the points at which the non-zero element is, the non-identity element lives, so to speak. Of course, if there's two of them, again, that gets identified with the identity element, in which case it disappears, we ignore it. And so the first claim, and this will be one of the things that we do in the second video, is that this is a CW complex. And a lot of you know what this will be. We'll talk about it in a second, with one cell in each dimension. Okay, in each degree. So the cell comes because if I, for example, take 3 points between 0 and 1 in ascending order, if I tell you which points, remember we worked modulo the symmetric group. So even if I listed, this is my x1, this is my x2, this is my x3, well, I'm gonna change it so that they come in order with a symmetric group action. Then the interior for sure, well, then the set of all such things where maybe x1 is coincides with x2, that's a simplex now. So that's taking this product of an interval cross to the k, but I'm quotienting by the symmetric group, and I'm just saying, well, we're gonna inside that K cube, we're going to just consider the K simplex. And it's the interior of that simplex, for example, which are the interiors of the cells. Okay. So, and now let's think about the boundaries. So, one thing that can happen is that two G's, and there could be others around, two G's collide and vanish. And this is right as xi goes to xi plus 1, the two G's, those 2 points would collide, their labels would add and vanish. And so that's a codimension 2 attachment. So that's going to be 0. The other thing that can happen is that a point could go here or a point could go there and vanish. And these are codimension 1, but they there's 2 of them, and so they will contribute 2 or 0 or -2, which is all 0. With mod 2 coefficients. Okay, and so from these facts, we get that there's a cellular homology. That the homology of this space is just Z2 for all I. Okay. And in fact, and we'll talk about this this space is homotopy equivalent to RP infinity. There's a good question, is it actually even homeomorphic? It's two skeleton, well, you've got these attaching maps, and for example, on the two skeleton, you've got a sort of a G and a base point attached. And so the attaching map isn't quite the same as for RP2. That said, you can imagine a homeomorphism with of that two skeleton in RP2, because I'll factor through the quotient by of this triangle, taking out that side, and then you see that this new construction is homeomorphic to the old one, and the new construction is exactly the RP2 inside of RP infinity. In any case, the theory that we'll do in the second lecture will say that this is at least homotopy equivalent to RP infinity. And so we know this homology already, so to speak. But actually, this model leads to a refinement of this calculation, which is not as well known as should be. That's why I'm giving these lectures. So here's a proposition first. And again, we'll elaborate, we'll use this. B delta NA is a topological abelian group through union. So the picture is just you take your AIs and you superimpose them. Of course, if we want to do coordinates, I've got my x1 through xk cross a1 through ak. And then I've got some y's. And all I'm going to do is going to take the union and yeah. So you can check that this makes the construction into a topological abelian group. Inverses, well, just take inverses of all the points, then with the same locations, and then things will cancel out. Other axioms just follow from the axioms given on A. And then here's the general fact that if G is a topological group, then its homology is an algebra. And so if it's topological abelian group, its homology will be a commutative algebra. In fact, we'll talk about in the third lecture, this will be a Hopf algebra. That's because of compatibility with diagonal maps. So yeah, so what we just said is that the homology of our P infinity with Z mod 2 coefficients is an algebra. I want you to take a guess. And of course, I think most people, knowing what the cohomology algebra is, say, well, that's a nice answer, and might guess that, but you'd be wrong. So it's not a polynomial algebra. All right, and to see that, what I want to do is make a little multiplication table. Mhm. And I'm because the another key fact is that the multiplication is cellular. That's pretty immediate to check in this case. So I can list my cells, and my cells are all homology classes. And let me just list them out geometrically. Degree 1, degree 2, degree 3. And okay, that's fine. You are seeing, and then the product is union, or superposition is the other way to think about the product. So you see that if I have a point in this cell and a point in this cell and I multiply them, I get a point in that cell. That's great. And I get every such point. Remember, for then a cellular multiplication, we want to calculate basically degrees. Degree theory is at the heart of cellular homology. But for every one of these, I'm actually getting it twice, because I don't know, if maybe I should have made these red up here and these blue down here. And this point could be the blue one and this the red one, or vice versa. And so there is a degree 2 when I write this. Similarly here, this is going to be degree 3. Here, it's fun to think about 2 points and 2 points. The number of ways that I could get a single picture from reds and blues while I'm coloring the 4 points, red or blue, choose 2 of them to be blue, then of course I'm going to get 6. And so in general, what we find is that the multiplication sins bi, or gives bi, if that's the I cell and the J cell, I'm going to get this binomial coefficient. Multiplying that's the coefficient of that cell. So this kind of algebra, and of course, these are all homology representatives. This is called a divided powers algebra. And so, yeah. And so we see that it's definitely not polynomial. At the prime 2, you'll often see that it's just its exterior generated by B1, B2, B4. So for example, B3 is the product of B1, B2. B1 times B1 is twice B2, so that's 0. So that's exterior. But that's what it's isomorphic to. I like to think of it as divided powers. And I like to think of it as on a single class B, B1, and then we've got the B sub i's are the ith divided power. So bi equals bi is one bit of notation. We'll probably keep those brackets around. It's traditional to use the square braces for divided powers. So yeah, that's a bit of a surprise, and that's a pretty picture. And let's actually so the homology of RP infinity is divided powers. And by the way, this fact up here, the fact that it's kind of interesting pedagogically that that we don't sort of do more with the fact that if G is a group, I mean, this is just some a simple diagram chase to show that if G is a group, then the homology is an algebra, and it's elementary. This could be done in first-year algebraic topology, but we tend not to because, well, it's hard to make examples. G being like a matrix group takes a while to compute the homology of. And we tend to want to go on to more and more structure rather than go so far into examples. But here we can actually make this as an example. And it's an example related to RP infinity. Again, if you take the fact that this is homotopy equivalent to RP infinity on faith, or well, next lecture will prove that. Okay, so that was fun. So we've got a divided powers on a class B, or sometimes I'll use E or something like that. Let's now move on to the next case. And that's B squared C2. Okay. So so here's a theorem proposition. There is a CW structure on, on this space with cells indexed by tuples of positive integers. Okay. So for example, this would be, and what those are is just the number of points that line up. So you group the points, which again, we're in the group of order 2. So each of these is just labeled by the non-trivial element, but I'm omitting those labels. You group them according to who shares their x coordinates. This is why we want to use the cube model rather than the sphere model. This alone is in a nutshell. And so then, like this example, that I would have 1, 3, 2. Okay, and it's a cell of degree. Um, well, the 1 point can go up in the line, but it's where the line is also can move. The 3 points can move up and down the line, and the 2 points can move up and down their line. And where those lines are rooted, where the vertical lines are rooted, also is a degree of freedom. Okay, so um, so these are the cells, and right. And then you want to understand the boundary. Okay. And once again, we can have a couple different things happen. Um, Points can again collide along their lines. And that's going to give a codimension 2 answer. For other coefficient systems, if I were working over the integers, 1 and 3 collide and they make 4, and that's actually going to be its own. That things don't vanish, but here with the group of order 2, um, so collide within on their vertical line. You can run off the top or bottom of vertical line, and that's going to be 0 mod 2. And finally, these lines can come together. The vertical lines can come together. And there, what you get is right. If I think of my my positive integers, let's call them CI. So I take my C1, CK, and then if, for example, the 1 and 3 line come together here, then I'll get, I add 1 plus 3, I'll have 4 points on a line, but there's once again going to be this binomial coefficient multiplying. So I'm going to have things like C1, and then I'm going to have the coefficient CI plus CI plus 1, choose CI, and that's going to decorate, well, sorry, this needs to be a coefficient out front. I'm going to take CI plus CI plus 1. Those are the number of points now restricted to that line, and I'm going to have this binomial coefficient out front, not a fraction, a binomial coefficient. Okay, let me rewrite that just a second. Okay, so that's the coefficient of the ith term where the I and I plus first lines coincide. Notice that that is the multiplication in B delta 1 C2. So in fact, this was Cartan's key insight, what allowed him to push through all these calculations remarkably early in the development of the subject, is that the cellular boundaries here of these iterated bar constructions are given by the multiplications in the previous stage. This multiplication is divided powers. What he shows is that the results is also divided powers, and with some combinatorial changes. And so he's able to sort of bootstrap it up from, well, not even RP infinity, just C2 itself to RP infinity to the next to the next. I'm not going to go through that calculation then. I'm going to tell you about an alternate approach to it. And these haven't been written up in this language, so that's one thing. This is a YouTube. You can always now, anybody who's interested in this story, we can, and I'll say this again a few times, there's things to work out in this language that would be a nice contribution, and anybody who's interested is welcome to reach out to me and work it out on your own, work it out together. So the proposition is that the homology in this case is going to be given by tuples, say, non-decreasing, of powers of 2. Oops. So for example, there's a homology class that looks like this, which coincides to the tuple, because I'm going to make them non-decreasing, the 1, 2, 2, 4. So this isn't a tight, every homology class is represented by a single cell. This one is going to be the sum of things where I can put the 4, I can sort of put these guys anywhere. So I'm just looking at all the ways that I can shuffle 1, 2, 2, permute 1, 2, 2, and 4, just using once for the repeats of 2. In other words, I'm not going to necessarily have, in this case, 24 cells. In fact, I'm not. I'm just going to have 12 cells because I'm not going to permute the 2s, so to speak. So I've got a sum of 12 cells, and the claim is that that is going to be a cycle. And for every sequence of powers of 2, we will get a homology class. Okay. And this is still it's still a ring. And so let me just say, moreover, homology ring is divided powers on the classes just 1, 2, 4, etc. Okay. So the class 1 is corresponds geometrically to a single point, which can be anywhere in the square. 2 is 2 points on a line. 4 is 4 points on a line. Okay. This is often called iota. It's the sort of fundamental class. It's the lowest homology class. It's also it ends up being spherical, and so it's the generator of the homology class. So this is the fundamental class of B2 delta C2. Um, and yeah, and we're going to have that divided powers structure again. And so again, the if I multiply the one by itself, I actually get zero. But you see these lists come up just as products. Okay, let's go for one more, and and this is the real payoff to see the well, we already see more geometry here than before. The combinatorics is about to get more fun too. So for B delta 3 C2, let's revisit the labels in our cell structure. Okay. So if I have a collection of points in a cube, they're unlabeled, but I can order them through using the dictionary order. So this one comes first because it's furthest to the left. This one's second, third, fourth, fifth, and sixth. Okay. Um, the second, third, and fourth all share their first coordinate, so you have to use the second coordinate to dictionary order them. So it's a non-continuous order, but it's still something you can impose. And then what I'm going to do is I'm going to give a sequence of non-negative integers, which tells me basically how far in the dictionary order did I have to go to distinguish these. So between 1 and 2, I only needed my first coordinate. Well, we're going to call that a 0 because, well, that's just the more natural thing to do for degrees. 2 and 3, they share their x coordinate, so I needed the y coordinate. And so I'm going to label that with a 1. 3 and 4 also needed the y coordinate. 4 and 5 needed just the x coordinate. 5 and 6 needed the y coordinate. Okay. So these sequences of integers label the cells that I just told you about well, this is again in B delta 2 C2. All right. But now those similar names in B delta 3 C2, you can have a similar story where, maybe these three are on in a plane, but don't share any further coordinates. Maybe these two actually share their x and y coordinates. So I would have something like 2, 0. The next three share their x coordinates. So going from one to the next and the next to the next, I go again, and and you could also do things where within a plane, I've got one point shares one coordinate with the next, but the next two share two coordinates. Okay. So how many coordinates you share gives a nice way to think about these numbers. And so we and so then these are again a claim that there's a cell structure there. And that's also what we'll be talking about just through the machinery of this. This is called the iterated bar construction, but we're thinking about it geometrically. And now let me tell you about the types of cycles which we get in this game. So, right. So you can have two to the I points which share a single coordinate. So two to the I points, dimension two, or I really think of this as maybe codimension one. Okay. I can also have, and this is similar to what we saw for the second degree. I can also have two to the I points inside a dimension one space. These are all parallel to coordinate axes. In other words, these share their x coordinate. These share x and y. So not just any dimension one or dimension two subspace, but these lines are parallel to the z-axis only. Okay. And then the other thing that can occur, much more fun, is I can have two to the I points which share a coordinate. So two of the k points share their x coordinate. And they are a union of two to the j groups of two to the I points, which each of those each group also sharing their y coordinate. So in this case, these are both on a line, okay? And here's where I think it's kind of fun to play with combinatorics. To this first group, we're gonna produce leveled trees. This first example, I'm gonna have a leveled sort of dyadic tree. With four branching at the root and then no further branching. Here I'm going to have a tree with the branching at the next level. Okay. There's a bit of choice here. I still haven't fully decided should yeah. But I think this is the right way to go. And then finally, here I've got my two to the j groups. Well, let me just make it accurate to the picture. Two to the j groups of two to the I points. There's two to j branches here and two to the I off of each one. Okay. And our previous cases also would be leveled binary trees for the one-dimensional case, well, and then the claim is that combinatorially, homology, mod 2 homology of this space, which is, remember, our B delta 3 of C2, is isomorphic to a divided powers algebra on these level 2 dyadic trees. Okay, and additive basis is that of forests with these trees. Okay, so that's the claim. This reads very different from Cartan, though it's not that hard to make the translation. These integers here, these indices, are what you could call this an alpha, say I, J, or I'm not even sure what. And that's this typical way to talk about this calculation. But I prefer the level 2 dyadic tree perspective because you see it's so well tied to the geometry of the classes. So in any case, this hasn't been written up, but it is something that I want to write up at some point and develop further. We're going to do that in a couple more lectures. I'll go back and fill in some details of how to prove that this model for Eilenberg-MacLane spaces indeed is a model for Eilenberg-MacLane spaces, and structure, more basic structures in the second lecture, filling some things in. And then in the third lecture, I want to talk about these homology calculations more. I want to bring in we see the power of this multiplication, but there's going to be a second multiplication and a Hopfring structure. So that's where we're going, but I wanted to share this geometry and combinatorics in the current lecture. So I'm going to